Hello everyone. So we are here for integral calculus and differential equations. It is the course title and the course code is Math 120. Okay, so you can see that we have two parts that are attached: integral calculus and differential equations. This part, that is differential equations, will probably start after your midterm exam. But before that, we must have to have the basic idea of integral calculus. So you know that integral calculus is a part of calculus, or in other words, we can say calculus can be classified into two categories, that is differential calculus and integral calculus. The differential calculus part, you have learned this thing in your previous course, that is in Math 110, and the integral calculus part, we are going to learn these things in this course, okay, that is in Math 120. So besides integral calculus, remember we have another part that is called differential equations. So differential equations are some kind of equations where derivatives are involved, okay. So at this moment we have to focus on differential calculus, and in this video I will try to cover up all the things of integral calculus, all the basic, how we can deal with the basic formulas of integration, okay. So first of all, by the time, I hope already we have the basic idea of differential calculus, okay. Now we are here for learning integral calculus. So mathematicians have been playing with the concepts of integration for ages. That means all the way back to the Greek times. But it wasn't fully established at that time until the period of Sir Isaac Newton. Okay? So in his time, it was realized that integration and differentiation, that is integration and differentiations, are actually inverse operations, just like summation and subtraction, multiplication and division. Integral calculus, that means integration and differentiation, are opposite of one another, okay. That means these two things are linked up. And this realization, that means integral calculus, that is integration and differentiation, are actually opposite or inverse operation, that is this realization actually paved the way for today's modern calculus, okay. So first of all, we have to know what integration is, okay. That means since Math 120 deals with integral calculus and differential equations, that's why let's try to start from the very beginning, okay. So we have to know what is integration at first, or what is the importance of integration in real life. So from the concept of geometry, we have learned how to find the area of a rectangle, how to find the area of a square shape. We also know how we can find the area of a triangle, or maybe some other shapes like polygons. That means we may have a parallelogram, we may have a trapezium, okay. So we know from the concept of geometry, we know that suppose for this rectangle, this is base x and height y, so the area will be xy. Similarly, since this is a square, let's say base and height are same, So area, you know that it will be x times x, that is x squared. For this triangle, you know that if base is b and the height is a, then area can be found by 1 by 2 base into height. So this is how we can find the area of a rectangle, of a square, or a triangle. Similarly, for other polygons like parallelogram, if this is b and this is a, we know that area is b times a. For this trapezium, suppose this is the height a and this is the length of the big side, that is, suppose it is b1, and it is the length of the small side, that is b2. So area can be found that by this formula, that is 1 over 2 a times b1 plus b2. That means you don't need to memorize all these things. We are just recalling whatever we have learned from our geometry. Okay, that means these are the common shapes. If we have polygon, okay, then just like rectangle, square, triangle, or other polygons, we can easily find the area. But now suppose we have a different shape that is not a rectangle, or that is not going with the common shapes. Okay, or suppose we have a function that is going with this curve. Okay, it is the function. So you can easily say that the area that we have here, that is not a rectangle, rather we have a curvature shape. Okay, so what should we do if we need to find the area for this type of shapes? Or for this one, what will be the area A? So these are the things that are discussed in integral calculus. You have to know that with the help of integral calculus, we can find area, volume, surface area, length of any curve. Okay, we can find the volume of a three-dimensional shape. We can find the area just like this one. We can find the length of this curve. So all the things, maybe two-dimensional or three-dimensional, can be described in calculus part, most importantly in integral calculus part. Okay, and you must know that differential calculus deals with the rate of change, and integral calculus deals with finding area, volume, surface area, just like that. So our question is how we can find the area for this type of curve, or suppose we have this type of curvature shape. So what we can do here, at first we have this shape. I am just drawing the same one here. Since we don't know, we don't have the exact formula for this one, so what we can do, we can just think about, suppose we have a rectangle here, we have another rectangle here, we have another rectangle here, just like this. Okay, so if we sum up all the rectangles, that means if we sum up the area of all the rectangles, then somehow we will get the area of this shape. But you can see we have a blank space. That means we are not getting the exact area. Okay, so what we can do, instead of taking 1 2 3 4 5 rectangles, we can extend the same idea. But this time we can take more and more rectangles. 1 2 3 4 5 6 7 8. So this time for this one we have taken 1, 2, 3, 4, 5 rectangles, but here we have taken 1, 2, 3, 4, 5, 6, 7, 8 rectangles. So you can easily say that we can sum up all the rectangles area, and we will get somehow the area of this curve from this part to this part, but still we have some error here. That means the area that we are going to find is not the exact area. We're getting the approximate part. Okay, so if we extend the idea similarly, if we take more and more rectangles, we will get the closer and closer accurate area. Okay, that means our we will get the exact area of this type of shapes if we take so many rectangles at the same time. That means the number of rectangles should be infinity. Okay, that means so that it looks like we may have the total area. Okay, so it is only possible, we can only find the total area, we can only find an exact area if it is possible to have infinitesimal rectangles. Okay, so now what we can do, just to find the area of that curve, I'm again drawing the same thing here. So we have so many rectangles. If you know that y equal to f of x, so this is y, that means f of x part, so this is acting as the height. So since we don't have any exact formula for finding area for this type of curvature shape, so that's why we are taking the help of this rectangle formula, or we can also take the help of a square or other things. But for this we are using this one, that is, if we have a rectangle, then the area will be x times y, that means base into height. Okay, so here for the first rectangle, we can think about it is y1 and delta x. So for the second integral, we have this height y2 delta x. So this is how we can go up to infinity times. So here the heights are not same always, because here we have one rectangle and here we have another rectangle. So the rectangles are different from one another, but this distance are same. So if we multiply, you know that area for a rectangle is base into height, so base into height, and if we sum up all the rectangles area, that means we will get y1 delta x, y2 delta x, y3 delta x. Similarly we can go up to infinity. Okay, so that means we will get the exact area if it is possible to go from 1 to n, and n is approaching to infinity. So since y is equal to f of x, so instead of y we can think about yi, it will be f of xi. So limit n tends to infinity, summation I equals 1 to n f of, instead of yi I am writing now f of xi delta x. So this is now known as the area. It says that we will get the exact area if we take more and more rectangles, and if it is possible to take infinity rectangles, then we will get the exact area. Okay, so this part is giving us the value of the area of any curvature shape. Okay, so if we add up all the rectangles area, then we will get the precise area. Okay, so for that curve, and now we can extend this idea with a new approach, that is, instead of using limiting concept, we are using this sign which is now known as integral sign. Okay, it is just like a long S. Okay, so it is called integral sign, and the function is f of x. Instead of delta x, we are writing dx from starting part to ending part. Let's say the starting part is a. I am defining it is x equal to a, and the ending part is x equal to b. You know that x equal to a is the vertical line. That means if I say that x equal to 2, 1, 2, so at this part there will be a line. This is a vertical line. You know all these concepts from geometry. If we if I say y equal to b, then this is giving us the horizontal line. Okay, so that means we have y equal to b, or suppose we are going to draw y equal to 2, then it is y equal to 2. If we need to draw y equal to -1, so it is -1. So here we have y equal to -1. So that means finally we can say that x equal to a are the vertical lines and y equal to b are the horizontal lines. So here x equal to, let's say we need to find the area under this curve, that is f of x, y equal to f of x above x-axis from x equal to a line to x equal to b line. Okay, so that means here we can place x equal to a, x equal to b. So that is now known as the common form. Okay, you can see this is called the integral sign, or let me write by another way. Here we can write this one as integration from a to b f of x dx. Here I have written, I have mentioned x equal to a and x equal to b clearly, but we can also write by this way. So if we integrate the function f of x over x equal to a to x equal to b in terms of x, then we will get a number that is defining the area. Okay, area under that curve from x equal to a to x equal to b. So this is the theoretical part, how integral calculus was evolved. Okay, so you can see that this limiting concept is being replaced by this integral sign. Okay, it's look like a kind of s, big S, but actually now we can say this is integral sign. And this symbol was introduced by Gottfried Wilhelm von Leibniz. He was a mathematician. Okay, so integral sign was first introduced by Leibniz. So you can see that since this integral sign is telling us where we have to start and where we have to stop, you can see x equal to a is the starting part and x equal to b is the ending part, and we are finding the area under this curve from x equal to a to x equal to b above x-axis. So it is now known as, so since we are finding the area from x equal to a to x equal to b from defined in a defined interval or region, that's why it is called now, it is known as definite integral. That means the integral where we have both lower limit and upper limit, that is called the definite integral. Okay, so here let me describe again. That is, we have integration from x equal to a to x equal to b f of x dx. So here this is called the integral sign. The function that we have here, it is the integrand, and we are integrating in terms of with respect to wrt with respect to x. Okay, that will give us a finite value. We will get a finite value, or we can say by this, it will be finally a real number, because the function is continuous from x equal to a to x equal to b. And after solving this integral by some technique, we will finally get a finite value that will be a real number that will define the area. So let's think about what will be this one, or how we can find this result. Okay, so here we have again integration from x equal to a to b f of x dx, and the geometrical concept again I am drawing here. So suppose we have the function y equal to f of x. This is any arbitrary function, and here we have a. A is the lower limit of integral part, and b is the upper limit of integration. So here x equal to a, let's say this is x, so x equal to a, and it is x equal to b. So x equal to a is the lower limit, that means we have the lower bound, and x equal to b is the upper bound. This is the figure from where we can say that we are actually finding the area of this function y equal to f of x from x equal to a to x equal to b. So since we are lucky now that we have this integral concept, so from this part to the rest of this video we will not be talking about rectangles, okay, or we will not be talking about this limiting concept, because we are lucky that already we have the modern calculus part. Okay, but whatever concepts here we can see, that is limiting concept, this is the fundamental part for integral calculus. So I have mentioned to you earlier that finally, if we solve this one by some techniques, we will get one value. But before that, we'll get a function. I am writing as it is uppercase F, that is capital F, and it is a small f. So remember, a small f and capital F are different. So we are often using this square bracket. Okay. So what we are getting? we can input at first b in the place of x, negative a in the place of x. That means finally, after the subtraction part, you will get a finite value. That will be the area under this curve from x equal to a to x equal to b. So here you can see that I have written one function f of x, capital Fx, and here you can see a small fx. So this capital F is called, it has a specific name, it is called antiderivative, or we can also say it is antiderivative. Both pronunciation is correct, so we can say antiderivative or antiderivative. So this is the antiderivative, and let's say this is the original function. So if we input b in the place of x, that means antiderivative at upper limit b, negative antiderivative at lower limit a, that will give us a finite value. That is now known as the area under the curve from x equal to a to x equal to b. Now let's focus on this antiderivative part. So what is antiderivative? So antiderivative, I'm mentioning antiderivative as capital F x, and the original function is a small f x. So what we are getting, if we integrate f of x with respect to x, we will get the antiderivative. So the process of finding antiderivative is called integration. Okay, the process of finding this antiderivative is called integration. But there is a relation between antiderivative capital Fx and the original function f of x. So let's say this is the original function. So the relation is, if we differentiate the antiderivative, that is capital Fx, then we must have the result, that is we will get back to the original function small fx. Or in other words, we can say if we integrate small fx, then we will get the antiderivative capital Fx. Okay, so derivative of antiderivative will give us the main function back. So this is the relation of antiderivative and the main function. Newton and Gottfried Wilhelm Leibniz, okay, that means Sir Isaac Newton and Gottfried Wilhelm Leibniz found that evaluating antiderivative, that means evaluating antiderivative or finding antiderivative is just same as adding up all the rectangles. Okay, that means whatever concepts we have for this one, that is limiting concept, we will get the exact area if we sum up all the rectangles. If the number of rectangles are infinity, then the area of that curve under that curve will be exact. Okay, but the process of finding antiderivative is called integration, and if we are able to evaluate antiderivative, then it must be same as the limiting concept. Okay, that means it must be same as the same as adding up all the rectangles, all the tiny rectangles. Okay, so this is the main concept of antiderivative and original function. That means if we differentiate the antiderivative, we will get the main function back. And whatever part I have described here, that is called the fundamental theorem of calculus. That means we are integrating from x equal to a to x equal to b f of x dx, and we are finding the antiderivative for this original function. So with upper limit and lower limit. So fundamental theorem of calculus says that just to get the area, we have to evaluate antiderivative at upper limit b, negative antiderivative at lower limit a. This will give us the finite value. That means in summary, I can say if a function is continuous from x equal to a to x equal to b, and we are going to find the area for this one. So we will get finally the antiderivative. So antiderivative at upper limit, negative antiderivative at lower limit is called the fundamental theorem of calculus. It is called the fundamental theorem of calculus. So whatever concept I have established here, that is ddx of capital Fx is equal to small fx. So first of all, you will understand if I show you one example. Okay, so by the time, I hope already you know that integration of x to the power n dx is equal to x power n plus 1 over n plus 1. Remember, this n is not equal to -1. So this is called the power tool. Okay, it is the very common formula for integral calculus. So suppose we have to integrate x squared dx. So using this formula, we can write x to the power 2 plus 1 over 2 plus 1, because n is equal to 2 here. So that means n equal to 2. We are just placing where we have n. We are just placing 2 where we have n. So finally, what we are getting? We are getting x power 3 over 3. Suppose we are integrating from 0 to 2. That means we have the upper limit and lower limit. So what we have to do? At first, try to figure out that the function that we have here, that is small f x. And finally, after solving this integral, whatever function we have found here, that is capital F x. So you know that this is called the original function, and it is called the antiderivative or antiderivative. So now check the relation, but at first I'm collecting the information. That is, here we have a small fx, that is equal to x squared, and capital Fx, that is found to be finally from here x cube over 3. So let's get back to the fundamental theorem of calculus. Suppose we are integrating a function f of x from x equal to a to x equal to b, where x equal to a is the lower limit, x equal to b is the upper limit, and finally we have the antiderivative f of x, capital F x. So just to find out the area, what we can do? We can at first find the antiderivative at upper limit, negative antiderivative at lower limit. So I am doing the same thing here. This is our antiderivative. So antiderivative at upper limit. Remember, we have to input the upper limit where we have x. So x is our input. So antiderivative at upper limit, negative antiderivative at lower limit. So what is our lower limit? Lower limit is 0. So finally, if we solve this one, we will get 2 cube by 3, that is 8 over 3, and this part, the second part, will be 0. So this is our final answer. That means it is defining the area. So you will understand how we can say this is area if we have a look on the geometrical concept. But for now, what I am going to tell, we are going to establish this relation. That is, if we differentiate the antiderivative, we will get the main function back. Okay, since I have mentioned that integration and differentiation are opposite type. Okay, so integration and differentiation are actually opposite. So the relation that we have, if we differentiate capital Fx, we will get the main function back. So let's verify. So if we differentiate the function ddx of that function f of x, let's see what happens. ddx of, inside f of x, we can now input x cube over 3. So since 1 over 3 is constant, we can pull out before the differential operator ddx. So here we have found this one. Now you know that differentiation of x to the power n, that is equal to nx power n negative 1. This is our very basic formula from differential calculus. So what we can do here, we can write 1 over 3. For this one, we can write 3x squared. Okay, so finally we are getting, if we simplify this one, 1 over 3 times 3, so we are finally getting x squared. Now have a look here. X squared is our main function, so that means it is f of x. So ddx, so from left side we are getting ddx of f of x is equal to small fx. That means we are able to verify this relation. That means if we differentiate the antiderivative, we will get the main function back, and if we integrate this function, we will get this one. Okay, so that's why integration and differentiation are opposite, just like summation and summation and subtraction, multiplication and division. Okay, you can think like that. Okay, so now let's have a look on the geometrical concept. We have integrated this function x squared from x equal to 0 to x equal to 2, and finally we have found 8 over 3. 8 over 3 has the numerical value, that is nearly 2.67. Okay, so that is a real number. So let's have a look here. Now we are going to discuss the geometrical concept. Geometrical significance. So what we are doing, we are integrating the function x squared from x equal to 0 to 2. X equal to 0 to 2 with respect to x, and finally we have found 8 over 3, that is actually 2.67. Okay, so let's draw the function x squared. So the function that we have here, f of x equal to x squared. So what we have to draw? What we have to do? We have to draw the graph of this function from x equal to 0 to 2. That means x equal to a to x equal to b. So let's do the same thing here. For drawing the curve, we can use this technique. X is our input and we will get finally y as output. Let's say f of x equal to y. So since our lower limit is given, lower limit is 0, so we are starting from 0. And upper limit is given, it is 2. In between 0 and 2, we can take any random value 1. Okay, the more values we will take, we will get the smooth curve. Okay, so that means the more points we have, the more the graph will be more and more smooth. So okay, let's input 0 where we have x. So 0 is squared, that means 0. 1 is squared, that is 1. 2 is squared is 4. But you have to understand that we are saying x as the input variable and y as the output variable. Why x is input? Because is it possible to get y without inputting x? No. So at first we have to input x, then it is possible to find y. At first we are inputting 1, then we are getting 1 as y. At first we are plugging 2 where we have x, then we are expecting for y, and y is found to be 4. So the points can be written in this way: xy okay, xy, that is for this part we can write 0 comma 0 point, we have 1 comma 1 point, and we have 2 comma 4 point. So let's plot all the points in Cartesian coordinate system. That is, we have x-axis and y-axis. So this is 0, 1, 2. Let's say this is 1, 2, 3, and 4. 1, 2, 3, and 4. So let's look at the first point, 0, 0. 0, 0 is obviously the origin. 1, 1 point. So 1 and 1. 2, 4. It is 2, and you can see this distance is 4. So here we have 4. So now we can join all the points. Now we have the function y equal to x squared, or f of x equal to x squared, this one. So you can see that we have the limit, lower limit x equal to 0, upper limit x equal to 2. So lower limit and upper limit, that is lower limit is x equal to 0, upper limit x equal to 2. These are nothing but the vertical lines. From the concept of geometry, you know that all this will be the vertical lines. So let's draw the bounds. So at first x equal to 0, x equal to 0 is this line. That means it is acting as the lower bound, and x equal to 2 is the upper bound. Now what we can say, we are finding the area under this function y equal to x squared above x-axis from x equal to 0 to x equal to 2, and the area will be this one. Okay, and this area must be equal to 8 over 3. So see how integral calculus can be applied in finding the area of any curvature shape. You can see the shape that we have here is just like this one. It is not a rectangle, it is not a triangle, or it is not going with the common shapes that we have. So the integral calculus, the concept of integral calculus is helpful for finding the area of this such kind of functions. Okay, from x equal to a to x equal to b. So this is what we can say, that the definite integrals, where we have the lower limit and upper limit, if we integrate the function, we will get the antiderivative, and finally we will get, finally if we apply the fundamental theorem of calculus, we will get the value, we will get one real number, and that will be an area under that curve from x equal to 0 to x equal to 2. So I hope you have understood the geometrical concept. So let's come to the point. Let's have a look on the properties of integration. So first of all, let's say we have a function f of x, and we are integrating from x equal to a to x equal to b dx. So this will obviously give us an antiderivative, upper limit b and lower limit a. That means f of b negative f of a. That is called the fundamental theorem of calculus. So try to recall these formulas every time. Try to practice the problems so that you can feel the fact of the fundamental theorem of calculus. So before discussing the properties of integration, I would like to point out two things. That is, suppose we have the integral, and integral can be classified into two categories: indefinite integral and definite integral. So what does it mean? Already you have understood that definite integral are those where we have the lower limit of integration and upper limit of integration. So this is called the definite integral. It will finally give us one finite value, that is the area. But if we don't have any lower limit and upper limit, but still we are integrating the function with respect to x, so we must get one antiderivative. Since we are integrating this function, we must get one antiderivative. Is that okay? So you can see that there is no lower limit and upper limit here. So that's why the limits and bounds are not defined. We can't be sure that where we have to start and where we have to stop. Okay, where we have to start, where we have to stop, we don't know for this one. So if in summary we can say that the integral where we don't have any lower limit and upper limit, that is called the indefinite integral, and the integral where we have the lower limit of integration a, upper limit of integration b, that is called definite integral. Okay, so first of all, since we don't have lower limit and upper limit for indefinite integral, so what we will get finally, we will get the function. But at the same time, we may have a family of function. That means we may have several functions. Okay, so we can input a constant c. So now, since we have indefinite integral with the antiderivative capital Fx, we are inputting a constant c. That is an arbitrary constant. It can be anything. It can be c, can be 0, c may be 1, c may be negative 1, okay, c may be 2, c may be e, c may be pi. So c can take any value. But now there may be a confusion that we have already established one part, that is ddx. If we differentiate the antiderivative, then we will get the main function back. But What will be the case for this one? With antiderivative, we have now plus c. So actually it is not affecting our result, because we know that differentiation, if we have several parts, using the sum rule of differentiation, we can separate this one, ddx of capital Fx and ddx of constant. So you know that ddx of f of x is actually the original function, and ddx of any constant, that will give you a value 0. So finally what we are getting? We are getting a small fx. So it doesn't matter whether we apply a constant here or not. That means it is not affecting our final relation. Still it is same. Integration and differentiation are acting inversely or oppositely. So this relation also holds for indefinite integral, and for indefinite integral we are getting a constancy. So I hope now you have understood. If we don't have the lower limit and upper limit for that integral, that is called indefinite integral. And already you know that if we have the lower limit of integration and upper limit of integration, that is called the definite integral. And finally this will give us a value, that will be the area under that curve from x equal to a to x equal to b. But for indefinite integral we will get the antiderivative, okay, with a constant c. That means it may be a function f of x if c equal to 0. If c equal to 1, we will get f of x plus 1, that is another function. If c equal to negative 2, we will get f of x negative 2, that will be another function. So we are getting several functions. That's why what I have mentioned, for indefinite integral, finally we will have the antiderivative, this one, that is a function, or it may be a family of functions, okay, depending on the constant c. So let's have a look on the properties of indefinite integral. First of all, suppose we have integral f of x plus g of x. That means two functions are summed up, and we are going to evaluate the antiderivative. So what we can do? Integration allows us to separate this one separately. Integration of f of x with respect to x and integration of g of x with respect to x. So the same condition holds for if we have negative here, it will be negative. Suppose we have constant with f of x, that means c times f of x here, and we are integrating with respect to x. So since c is the constant, we can pull out c before the integral part. So the result of left part and the result of right part is same. So this is another property. Now have a look on another part from definite integral. Suppose we have the function f of x. We are integrating this function from x equal to a to x equal to b with respect to x. So you will understand what I am trying to say. X equal to a, that means the lower limit is here, and suppose this is our upper limit, x equal to b, and the function, it may be a curve. So in order to find the total area, somehow for the simplicity of our calculation, we can think about another part, another vertical line, x equal to c. That means now we have one region, we have another region. For getting totality, let's say this is A1 and it is A2. So the total area will be A1 plus A2. That is equal to A. So that means what I am trying to say, we are integrating from x equal to A to x equal to B. But for the simplicity of our calculation, suppose we have another vertical line here, x equal to C. So what we can do here, the total integral x equal to A to x equal to B will be split up from x equal to C once plus C to B. So this is how we can think about. And the function is same, f of x. So integration from A to C, f of x dx, plus integration from C to B, f of x dx. So whatever result you will find for this one, for the left side, same result will be found for the right side. Okay, so these three properties are very important. I have mentioned here for indefinite integrals. You can also think about for definite integrals. Okay, that means we have suppose lower limit and upper limit, but the properties are same. So now let's have a look on the contents that we have in our course Math 120. Okay, that is integral calculus and the differential equations. So let's have a look on the contents of integral calculus. Whatever we have discussed so far in this video, that is the very basics of integral calculus. This is the basic for indefinite integral and definite integral. We have discussed the geometrical concept so that you can understand that integral calculus deals with area. But later on, you will understand that not only area, integral calculus is applied to find the volume, surface area, or arc length. Okay, that means I am saying integral calculus is applied to find the volume of a three-dimensional shape. It is applied to find the surface area. It is applied to calculate the length of any curve. That's why it is called arc length. Besides all these things, the common part is also finding area. So integral calculus deals with all these things. Okay, so let's have a look on the contents of integral calculus, what we have in this course. So first of all, we have to know what is U substitution method. You can also consider it is substitution method. Okay, and then how we can find the definite integrals, how we can find the result of the definite integrals and indefinite integrals, we will learn then. Okay, that is more specifically I can say evaluating indefinite and definite integrals using the technique U substitution method. Then we have to know what is integration by parts. Then our focus will be on integrating integrating trigonometric functions. Then we will discuss one important topic that is called trigonometric substitution. Besides integration by parts, we have another technique that is called tabular method. That method is not applicable for all functions, but we will try to discuss this one because for some problems this will be helpful. It will be a speedy process. Okay, already you know that this course integral calculus and differential equation, that means math 120 is the combination of integral calculus and differential equation. So after successfully completing integral calculus, we have to move to differential equations. So differential equation is actually based on integral calculus. Okay, so that means without the ABC of integral calculus we can't start this part. So somehow you will see that whenever you have a differential equation, at that for that for solving that differential equation, maybe the concept of tabular method will be helpful. Okay, so that's why we have to know tabular method besides integration by parts. So okay, we have integration by parts, then integrating trigonometric functions, trigonometric substitution method. Then we will have another topic, that is how we can integrating rational functions. Then we have to know how to integrating improper integrals. After completing improper integral concept, our focus will be on gamma function, or we can say integrating gamma function and beta function. Okay, so these are the concepts whatever we have in math 1 to 0. But remember, the first part should be, you have to start from the very basic concepts, that is from U substitution method, because this is the very fundamental technique that is applied very every now and then. Okay, so U substitution method, then how a U substitution method can be applied to find the antiderivative for indefinite integral and to find the area for definite integral. Okay, then we have to know integration by parts method. At the same time, we should know tabular method. Then our focus will be on trigonometric functions, how to integrate trigonometric functions. Another substitution method is called trigonometric substitution, that will be also discussed here. And then we will discuss about integrating rational functions. Then our focus will be on how to integrate improper integrals, and finally integrating gamma and beta function. I hope you have understood the contents.